all for coming. So I'm going to be talking about building data pipelines without using dependencies as much as possible. So who am I? I've been doing Elixir since about 2017. Prior to that, I spent about a decade of my career doing Ruby. A lot of that in my time in Ruby, I was actually doing some data pipelines, some complicated multi-stage data pipelines, but queue-based. And one of the things I want to talk about today is like, now that we're in Elixir and have access to the Erlang VM, what if we actually trusted the runtime to actually do a lot of the work rather than actually using dependencies? With an asterisk. And that asterisk is, what if we modeled our domain, our data domain, around events to help us with that? So a little bit about the story. Some of you might remember a health crisis a couple years ago. Through some really crazy happenstance, I happened through that time to work on some data pipelines for some contact tracing efforts for a U.S. state. And a couple years on, this same Department of Health was working with Ratio Public Benefit Corporation, needed some help, and Ratio brought me and my business partner in to help build an application. So what they had was 2 years of healthcare data, millions of COVID healthcare results. And it turns out a Department of Health that has test results, where those tests were administered, and continuity of care documents can put together those things into interesting statistics on comorbidities, conditions that actually contribute to the outcomes. But this data was in a bunch of different places. So they had tens of millions of records that would be coming in poorly normalized CSV files, pipe delimited, but fundamentally CSVs. But the actual patient data was split across 6 health information exchanges, and the performance characteristics of these were pretty bad. Very low concurrency, sometimes 10 minutes timeouts, and that actually might make sense because some people don't actually have a lot of health conditions. Some people have years of health conditions that might actually be the patients that the epidemiologists really want to see their data, but they have lots of data spread over many years. But we also have new files coming in daily because COVID still is a thing. And because this whole thing is about comorbidities, the actual data in the test results is actually very important. So sometimes the most important record to process is something from 2 years ago. Sometimes it is actually a test that just happened because it is actually in a hospital. So this is an application that we need to build. And so we're going to be building a data pipeline. But really, what is the data pipeline? There's a lot of different terminology. There's a lot of ways that you can model a data pipeline. And if you're familiar with traditional event, map, reduce type operations, you might use certain terminology. If you're familiar with streaming, audio-visual, you might use different terminology. But one of the things that I have found working with teams is that one of the things I hear a lot is, well, there's a library for that. And more typically, well, where's the library for that? Where's the library that I drop in and actually can do this? And typically, what people mean by that is, where's the task queue library for that? Because I have work to do. Obviously, I need to push it to a queue so that something can handle it later. And languages have it. Many languages, I would say probably any modern language should have some sort of task queue library. Elixir has some great task queue libraries. But in my mind, a task queue is really great when you want to offload the persistence of some amount of work to some trusted third party, perhaps because of some considerations of how you want to process, when you want to process, but also because you might not actually trust the runtime for managing asynchronous work. And in this case, this problem is not, in my opinion, a good fit for a queue. Please, if you have this sort of problem, don't push 2 years worth of data to a queue with 10-minute timeouts that is going to take months and months and months to process and expect to have to reprioritize it. It's just not a good fit. But again, what if we trusted the runtime? So what type of capabilities are we going to need? So we have CSVs arriving daily. They're coming into S3, so we have notifications via SQS. And in those files, we have lots of COVID test results. Those, based on that data, there's patient data, again, in 6 different APIs. And in that data, in that API, what we're going to get back is links and references to continuity of care documents that are going to be in different APIs. So how are we going to start to solve this problem? So Elixir gives us task. It also gives us spawn. We can actually just spawn processes and build things ourselves. But I'm going to skip over that. Task is really great for offloading, maybe not offloading some persistence and guaranteeing if the VM restarts, maybe not guaranteeing that it's going to complete, but it's giving you great facilities for this. You could build an event loop yourself. Earlier versions of the slide, I did that, but I was like, I don't have time. So let's skip straight to a gen server. So gen server is a great abstraction over async run loops with explicit messages, receiving messages, handling them, depending on the type of message you pass. You can say that you need to get a reply, whether that reply is given immediately or the gen server offloads it to some other task and eventually replies. And you can dispatch directly to a PID. If you have a name in a gen server, you can use some of the gen server functions themselves to do that. If you only have a PID, you can use those, but you can also send. And Erlang gives us a really amazing distributed event bus for message passing, not just a message bus, but a distributed one. It's actually pretty amazing. And one of the things that I think is so powerful about this is that the callbacks, when gen server calls your callbacks, it is actually functional and synchronous. So if you have a load of messages, a gen server is not going to be handling that concurrently. It's going to be handling each message synchronously, first in, first out. And we can monitor those processes so we can know that they die and possibly restart them. We can link to them so that if the process dies, you explicitly get you share that exit signal. So if the child that you start dies, you will be stopped, and vice versa. And it's a pattern. It's so common that we actually have shorthands for it: start link versus just start. And again, because these are such common patterns, we have these things in the library to actually build this. Supervisors to manage processes, restart them when they exit, with a really nice API. And important in this is that gen servers are actually agents for holding state, particularly state in memory. So you can offload state to a database. You can offload state to Erlang term storage, sort of like and other databases type things that the VM gives you. But when you have state in memory and state that is mutating based on messages, you have processes or the agency for holding state. And they're also the agent for actually designing concurrency. So, okay, so we have processes, wonderful. Data pipeline, wonderful. So, great, we can have a process and we can call out on a timeout to SQS, get the new messages, process those messages, get the patient data. But we actually, again, the back of napkin estimates are going to be like, it's going to take at least 8 months to process this data. Some of the health information exchanges may be up to 2 years to access the backlog plus the stuff that's coming in. So you don't really want to block a process for 2 years. Not so great. But we do have a process. Maybe there is actually a process here. So what is this type of data? So again, it's like the actual data is pipe delimited, but we can think of it as CSV parsing. And we look at a file, and great, we have 10 million rows. Again, we probably don't want to process this synchronously, all in one, blocking the memory, loading the entire 10 million rows, processing them, doing the next step, doing the next step. So let's talk about streams. So, enum operations load everything into memory. When each step is done, it might release that memory, but you actually have or previous steps might be released, but you actually are holding one big thing into memory. But Erlang also gives a stream, which is actually amazing. So a stream might load a batch into memory, but as the batch is proceeding, previous batches, smaller batches are being released, and each step is actually making sure that the previous steps are released. And streams are usually more memory efficient. You can find ways to make them not, but usually they're more. But they're also not concurrent unless you pass them to task. Once again, task gives us async stream. Suddenly, you're concurrent. And using up to all of your schedulers, all of your cores, you can configure that. Twice your cores, up to some amount of your cores. Suddenly, you're processing this concurrently and actually much, much faster. And also, if you need some actually management of when these tasks complete, you can actually swap out task with task supervisor. Suddenly you have facilities for waiting for tasks to complete. You might not wait for the entire stream to complete, but you can say, if I've started a task, I would really like the VM to allow that task to complete before we actually stop in order to do a restart. And this is amazing. Having done a lot of things in Ruby to do this type of thing, this is amazing. But streams can also be application specific. The VM gives you stream resource and stream unfold. And we can use those to emit batches, emit rows, or emit batches to the stream, keep a cursor so that the next time a batch loads, we know how to fetch the next batch. If the stream actually opens resources that actually have consequences, like opening a file, opens a file descriptor, which is a process that might not automatically be closed. Stream resource gives us the facility to clean up after ourselves. If you don't have that, stream unfold is really great. So practical example, ecto-repo stream has some opinions. You have to have an ID column. You are going to be iterating over that, the batches loading those in ID ascending, and you have to consume the entire stream in a single transaction. And you can do this if you're loading tens of millions of records. You might want to set a very high timeout on that transaction, because by default, it'll be killed after 15 seconds. But we have stream resource and we have stream unfold. And I won't spend too much time on this because this is one that I have written and used, but there are other examples on the internet. With newer versions, I would probably use stream unfold. If you look on Hex, you will find a library to do this. This is actually great. And this is where I might actually use a library, but you can write it yourself. It's really not that many lines of code to do this. In our case, again, the RCSV parser is more lines of code, and lines of code that I'm not contractually able to show on a slide. But conceptually, we have a file in S3, XAWS stream, can stream that by byte chunks, but we're doing CSVs. So stream allows us to transform it to sort of chunk those and then actually split on line endings. So now we have a stream of CSV rows. We can take that string again because we don't have mutable state. If you take one off, the stream itself is still the same original stream. So we take one off, suddenly we have the header. Then for our actual operations, we drop one, so we drop the header. And now in our pipeline operations, our stream pipelines, we can actually zip those together, process them, parse them, handle a bunch of error cases of, is this actually UTF-16 or UTF-8, which actually was a thing, depending on the file that actually happened at whatever time it was, we had to actually check. We can zip them together, suddenly we have rows. So great, we have pipelines. We have processes, we have streams. Suddenly we can add more processes. So we can actually be processing the CSVs, getting those test results, and reaching out. But now we have a bunch of different processes that are running. Now we need to figure out how does each process need to know what's going on. So you can do this naively, but if you have a bunch of different processes, they're all asking, give me the next work, and they're just asking for the database, a bunch of them are actually going to be doing duplicate work because they're going to be getting the same rows out of the database. So, but it's great. We have processes. We can solve everything with processes all the way down. But these processes need to talk to each other. So once again, when you just start a gen server with the default parameters, it just gives it, it just gives back a PID. It doesn't actually give you a name, or it doesn't give you a way to do that by name, but we can give a gen server a name. And we can give it one thing to know is like when you give it a name, that name needs to be unique for the certain node. But given that name, we can actually dispatch to this gen server. But we can do this ourselves. We can actually just say, hey, if we have a parent, we're starting a bunch of children. When you start them, the parent actually gets back the PIDs. They can just keep the PIDs and know how to dispatch. With a bit of finagling, say maybe we need to start a child and say, oh, by the way, this is actually my PID. Suddenly the children can know about their parents and actually message back. And you can do this. This seems like a bit of coupling. We actually are coupling this code together. We have a bunch of processes that won't work in isolation or are not going to work in isolation from each other. But this seems like not the best type of coupling for writing an application. But you can do it. But once again, Elixir gives us registries. This is a unique key registry, so the worker name needs to be unique. One thing is the registrar, the process that actually does the registration is the thing that owns it. So when the registrar disappears, the registry receives that messages and message cleans that up. So this is probably not what we're gonna want to do. But again, so with a duplicate key registry, we can have workers with the same name. But once again, in this case, I'm doing this in IAX. When the IAX PID closes, suddenly the registrar uses the information. But with a unique key registry, Elixir gives us the via tuple. We can just use that via tuple and say, hey, I'm going to register this process I'm going to start it. The name is going to actually be registered with this registry. You can use strings now. You don't actually need atoms to name things. You can actually use strings. But once again, this is a unique registry, so all of the workers need to be named something different. But now the register is the PID itself. So the registry is actually only keeping information about the PIDs that are actually alive. When the gen server closes, the registry cleans up. Suddenly, the registry is cleaning itself out. And again, this will only work with a unique key registry, but the init callback of a gen server is running in the PID. So with a duplicate key registry, you can actually build a registry that can actually be a non-unique registry. You say, give me a worker, and great, it'll give you back the workers. You can choose how to dispatch. But that only works on a single node. So what happens when we're actually using distributed Erlang? So Erlang does give us the global registry that uses a mutex across the entire cluster. When you actually are mutating the registry, it locks the entire cluster. And Elixir gives us the global tuple shorthand. So suddenly we can use globally unique registration. And it can be retrieved with the information about what's in the registry can be retrieved via the global module, the global Erlang module. And there's reasons not to use this. There are not reasons not to use this. But as an iteration, I would say this is actually, and when you're working with like small clusters, this is actually a very, very useful thing. When you're like, well, we're going to be locking a mutex around a cluster of 2 or 3. Great. But again, this does have some caveats. So when you're actually registering them, when you're actually using the global module directly, and you're registering, when there's a duplicate, one of the processes will be automatically stopped. And you can have callbacks. You can use callbacks to control this. But by default, it's just going to pick one, and one of them is going to stop. The shorthand in Elixir, the global tuple, isn't going to do this. It's going to actually give you back an error. Hey, when you start, it's going to say, no, something's already registered. Don't do this. If you have 2 nodes and you are able to start the same globally addressed process on both of them, you then join the clusters together. The global registry says, well, great, there's a conflict. One of the processes is going to die. And very naively, we can ignore the error and say, well, it's running somewhere, whatever. But supervisors don't automatically get notified about processes that are stopped or that die on another node. So in order to use this resiliently, we actually need to make this more complicated. So if in order to use global resiliently in a cluster, you're probably going to need a non-uniquely identified process on each node that is doing the registration, the global, handling the conflicts, registered for node membership changes when it's watching a global process on a different node and that node drops. Something's going to need to restart it, suddenly things like that. So this is actually where I would start to use a library. The last time I tried to use Highlander, I ran into some issues, but it actually is a really great place to start, particularly for the type of things that you would actually use. And again, it might actually just work. But this might also be where I would want to use some sort of eventually consistent registry. And there are a bunch of them, each of them with caveats that I don't really have time to go into. But these are great. So assuming we can use global, great, we can have a cluster and start, at most one type of each worker named important worker. In our case, that's not really going to work because we're going to have multiple of some types of workers. But with global, we can say, great, we have supervisors. We can globally name supervisors. Each globally named supervisor is going to run in one place, and it's going to start its tree of processes, and that might actually be what we want because we might want to do local message between locally coupled workers to actually be local on the node. Or we can let our web workers be web workers, whatever our dashboards, and scale an actual data pipeline node much differently. And this is not really if you're deploying to Kubernetes, this is really not what Kubernetes is going to want. But this is actually a very powerful thing and actually can greatly simplify things. It is much simpler when you're running out of capacity to make a configuration change and suddenly you have 16 cores rather than 18 or 32 cores rather than 16. This can actually make it much simpler to actually build a resilient data pipeline. So back to these CSVs. So we have data in them. We have basically a patient index, a master patient index. We have when it was collected. And we can, build a table. Put this into a table, wonderful. We're gonna eventually find documents about these, and so we're gonna have things. And we can build a process that does this, that says, given a path to a file in S3, stream that async, so we actually do concurrent processing of each row, and insert some test results. But we look closer, and there's actually some very non-normalized data. John Doe might be John D. No, John Doe is John D. Doe. It's the same MPI. But there's also a lot of things. But these are the sorts of things that you can actually solve functionally. So not the most interesting. You can actually solve this functionally to start to normalize the data, to fix the inconsistencies. But we also have problems like we have different master patient indexes, but this is probably the same person. This might be a father and son. It's probably the same person, having worked in a lot of healthcare data now over the last 4 years. But it's great. We can actually start to build more stream operations, more concurrent stream operations. We can stream the file, try to identify and maybe deduplicate who the patient is, combine records, then insert the test results. And we can actually start to normalize our database, actually take the name out of the test result and actually maybe start to put more of the person metadata into a patient record. And then we look at the next file, and it is actually, the files are not discrete. Again, this is 10 million rows-ish in each single file. There's not that many per day. There's not that many test results per day. Sometimes records do appear, or they disappear in one file and they come back for some strange reason. All sorts of things that if you've actually worked with data pipelines, you'll expect, like, whatever you think will go wrong with the data, it is going to go wrong with the data. But great, we have new operations. We can actually start to try to filter out rows that we've already processed. But now we have a problem of how do we do this? Well, If we start to model each row in a CSV not as a test result, but if we start to view it as some sort of event, a data event, we have an event that happened that implies that there is probably a new test result. Then we can save off the raw data, and actually now this is a much simpler operation because it's not about this part of it is not about deduplicating the patient. It's actually about just deduplicating data. Have we actually seen this row before? Maybe an update column changed, but we don't care about the update column. We actually can take a subset of the data, use hashing algorithms to actually like hash to some string, and actually put a unique column on that and let the database tell us, like, not allow us to put a duplicate record in. And with this, we can start to say, okay, stream the file, filter the existing records, which is actually more just based on checksums, insert raw test results or events. Now we actually can build a thing that streams through those, inserts the actual test results. And this is starting to look like not a data pipeline, but several decoupled data pipelines. But now we have a problem of, great, we have multiple sort of producers of things that need to be processed. Now we need to know, have we actually processed these things to get to before? And we can start to model this with just more metadata. Like, have we processed this before? Was it successful? Was it an error? How many times have we errored? And start to actually use SQL to model, like, how do we actually know whether something should be processed? Should this be delayed? Things where there was an error, but the error happened within the last hour. Maybe it's more important to actually get a hospital record through the data pipeline. Maybe delays could actually happen tomorrow, something like that. And we can, again, use sort of normalization of tables to actually separate the concerns of the data from the actual concerns of the actual data pipeline. We can introduce processing events and use where not exists queries, and be very careful about our indexes to actually make this performant. And this is like the very, very basics of event sourcing. But it's something that you can actually build yourself, and I would actually recommend that you do build it yourself, because when you actually get into something like commanded is very confusing. And if you were going to actually get into commanded, I would definitely recommend at least once, even as a proof of concept, having tried to solve the problem yourself so that when you actually run into the edge cases, you can actually know what's going on. So what type of capabilities can now emerge from this? So we're streaming through test results. We need to look up continuity of care documents and insert them into the database so that we can actually, so that another data pipeline will pick them up and start to process them. But actually, we actually have 6 endpoints that are working across different APIs. And actually, we have different concurrency constraints about each of those endpoints. And these are different data pipelines that can be started independently, configured on the fly. Use supervisor to say, I would like you to start 3 of these processes. Now I want you to add another one because we got the permission to bump the concurrency up to 4, things like that. And we could have a process that is looking for unprocessed data and pushing them. But now we actually have a dispatch problem. Like, one, the processor now needs to know what the capacity of its downstream things are. So in my experience, more demand-based approaches can actually be modeled to make this more resilient. When a process has the capacity to do work, it can use a registry to ask, I would like more work. And then if the producer already has batched new records, it can just reply with saying, cool, do this. If it hasn't, it can now look up new batches and, well, save off the fact that a worker is ready to do work and what work that is through actually just the PID or the sort of reply and say when new work comes in, it already knows that there is a worker ready to do work that has capacity. And what does this look like? A supervisor with a producer process and a bunch of actual workers. But what happens, this is not our case, but what happens when you actually have data coming in pushed to us? We have no control, and we have no control over the throughput of this. Webhooks, maybe you actually do have some sort of queue-based thing, but you actually don't have control over it, or for various reasons, maybe for cost reasons, you actually need to keep some sort of cost down, so you actually need this queue to be small. So you could actually just say, hey, a message is received. It goes into some sort of orchestrator process. It pushes it to available workers. A more demand-based approach, the orchestrator is receiving new data. The processors are asking for work. And if the new data is, if the demand and the forwards pressure are mismatched, maybe the orchestrator actually saves off, keeps the new events in its state until the demand, there's enough demand to build it. And this is Broadway. This is actually Broadway. Broadway actually introduces a couple more layers, or actually GenStage introduces a couple more layers of supervisors and things between the consumers and the producers. But at a high level, this is what it's doing. But again, we have slow processing. If we did have forwards pressure, we still would have slow processing. So this is where maybe we could push back. Is there the possibility to push back, to push the back pressure upstream to say, please slow down? Maybe the upstream thing can actually do more caching or more saving off and actually adapting to our capacity. Or maybe we can start to turn the forwards pressure into back pressure. The event handler can just save off events into a database. We have a producer process that is actually looking for unhandled events, using the back pressure of the slow processors to know when things can be reached. And again, use sort of capacity planning in order to actually solve this with, buying more cores, things like that. And we can, again, scale things very differently. Scale our database, scale our web workers to receive events or whatever that is, scale the backend in order to handle the events in a reasonable amount of time. But this is actually starting to look a lot like a task queue, actually. This might actually be where you want a task queue. This might be where you want to drop in Oban. And this is where it's sort of like, are the events important? Is the fact that an event happened important, going to be used for reporting, going to be used for SLA reports, service level agreement reports, things like that? You might still actually want to model this yourself. And if you're already doing that with the domain, you could drop in Oban, or you could actually model this with processes. Concurrency limits, processes. You have processes. Start more processes. Putting it all together. A few separate data pipelines, but not a whole lot of processes. We have an SQS poller that's calling out to look for new things in S3. When that happens, it can pass that message on to a CSV importer. We actually want to decouple that because we actually would like to deploy continuously. So we would like CSVs. We don't really want to block the CSV importer with actually doing the processing of each row and knowing what's in it. Just get that done as soon as possible because we have a separate pipeline that can look for unparsed, data events, process them, decide what is actually a new patient, what is actually a new test result. Now we have test results that can actually go into a separate set of queue. We can have 6 different pipelines, one for each health information exchange, that is really just getting the information about the documents. And the information of that documents can now go into 6 new pipelines that are all scaled depending on the actual capacity of the external resources. And this all runs on a single EC2 instance, which is really nice when you're managing things. So thank you very much. Hopefully this has been interesting and helpful. like many people who have talked, I also am a part of a consultancy. I'm a two-person consultancy, Reflective Software. You can find me on GitHub. The personal one is more for pull requests, but you can maybe find relations to other work that I've done. A lot of the open source stuff that I'm doing is actually under an organization, Synchronal. And if you're interested in doing work in healthcare in Elixir, you should probably take a look at Ratio. They're actually doing really great stuff. So thank you so much.